How many of you have taken a class with me before? Okay. Humor me and laugh during this joke, even if you've heard it, which you have. The first time you learn thermodynamics, you don't understand it. The second time you learn thermodynamics, you think you understand it. And the third time you learn thermodynamics, you're comfortable with not understanding it. I didn't make that up. Someone else did. I don't know who they are. I'm sorry, I can't give credit to them. Normally, I do give credit because I'm a professor and academics give credit. Okay, in the last couple of classes, we've been talking about pairwise interactions. Pairwise interactions occurring in air or vacuum. But when interactions occur in a medium, like a solvent medium, we actually have to be aware of some of the thermodynamic aspects of heat and mass flow between different regions of a system, and also multi-body effects. The fact that we have pairwise interactions between molecules in a vacuum, but in a solvent we have pairwise interactions between that molecule and all the solvent molecules, and then the effects on the solvent molecules sometimes propagate to other molecules in the system. So we're not going to spend a lot of time on thermodynamics in this, well, I shouldn't say that. Depends on, I'm going to spend a lot on the thermo part, not necessarily the dynamics part. But today we'll give you just a few arrows in your quiver for felling the thermodynamics beast. And what are the effects of taking a molecule and taking it from a sphere or a vacuum and putting it into a solvent? Well, there are a couple of things that happen. In two neutral molecules in a vacuum at a reasonable temperature at which the molecules are free to rotate if there's a dipole will always attract. But in a solvent medium, there is an additional work that's required to displace solvent molecules that may be solvating those solutes. And there might actually be a repulsive force in a solvent. So this is the first of four insights here when we go from vacuum to solvent, is that molecules may repel. Even neutral ones. If the work to displace the solvent is greater than the energy gain of the approaching solute. By gain, I mean increased favorability. So even though energies get more negative when the interaction becomes more favorable, by gain I mean, yeah. The gain of approaching solvent. So gain becomes more negative. The solute can structure the solvent. What do I mean by solvent can structure the solute can structure the solvent? If you take a methane molecule or a bunch of methane molecules or a droplet of oil and you put it in water, does it just swim around freely with the water molecules being totally unaffected by it? It doesn't. The water wants to maintain its favorable electrostatic interactions with itself and minimize less favorable interactions with the solute, so the solvent molecules may reorient around, in that case, a hydrophobic solute. And just to draw this in a conceptual way, picture some solvent, and imagine that these molecules have some anisotropic shape. Just picture them as lines, which may represent, say, the dipoles. And then you put some unlike molecule in here, and you might get some structuring effect. This could be, for example, what happens when you drop a sodium ion or chloride ion in water. You might have the oxygen atoms point toward the sodium atom for increased Coulombic bonding. In the case of chloride, you might have the reverse. And this could be, for example, a hydration shell. And these could be up to 10 times the ionic radii, with lifetimes of nanoseconds all the way to hours. Depending on the size of the solvated ion or the charge of the solvated ion. For example, aluminum 3+ in water has a big solvation sphere that persists. The closest water molecules to the aluminum ion actually are there for quite a long time. Experiments have been done that have shown that they persist there for up to hours. The solvent can change the solute too. So the dipole moment and the ionization state can be solvent dependent. What's an example of this? Suppose you have ammonia and you put it in water. And the ammonia is basic, so some acid-base equilibrium is going to tell us that some fraction of those ammonia molecules will take on an H+ from the water, and that will change its dipole moment and ionization state. Solutes also break apart the nice structure that a solvent has. So as the solvent bonds with itself, if you put a solute in there, it has to make room. It's like trying to get like a fourth person in a three-person couch, and people kind of have to make room, and you break the bonds between the people that are already there. So the solutes break bonds between solvent molecules. And this is called cavity formation. You can actually use the concept of cavity formation to approximate the amount, or you can use it to approximate the self-energy of a molecule in a solvent. So this is a quick and dirty way to calculate the self-energy, which, as we learned last time, is the sum of the interaction energies of one molecule with all the other molecules in the system, if we consider just the nearest neighbors in a solvent. And what we're going to do is calculate the number of bonds that are broken by creating the cavity, and the number of bonds that are formed when you put a new molecule in its place. So those are our 4 items here. We don't have a 5th item. These are the 4 principal considerations. Okay. Estimate the self-energy mu superscript I of a liquid based on this concept of cavity formation. So for close-packed systems, a solvent molecule has 12 nearest neighbors. What I want you to picture is a ball pit at Chuck E. Cheese. Or a ball pit, I don't know if Chuck E. Cheese still exists. But if it doesn't, picture a ball pit, which is like a pool full of multicolored plastic balls. Does everyone know what I'm talking about? Yes. Okay. And these ball pits are full of regular balls, smashed balls, arcade tokens, and pee. And when you create and if they're perfectly, some zones of this ball pit will be perfectly crystalline, where you'll have a perfectly close packed arrangement. Most of it won't be like that, but picture that it was perfectly close packed arrangement. And you reach in there because you're trying to get to the bottom where the tokens, where the high school ball pit lifeguards are, to prevent horseplay, and throw tokens in there. At least they did when I was a kid at Chuck E. Cheese. And you reach in there like this, like you're doing the breaststroke, and you push apart the ball pit, the balls in the ball pit, and you're breaking the bonds, and then you're putting a new ball in, and you're covering it back up, and it forms a new crystalline phase. That's what we're doing. A perfectly crystalline ball pit has 12 nearest neighbors. Each ball is touching 12 others. Is this always the case? No, just for spherical molecules. For water, this number would be 4. In a perfectly crystalline water, like single crystal of ice, for example. And is it always going to be 12? No. These molecules in a liquid phase are going to be fluctuating all over the place, and the number of molecules will change over time. But just give it to me, okay? It's 12. Okay, so the energy taken to break 6 bonds is going to be negative 6W of sigma. What is W? W is the pair potential between 2 molecules. And what's sigma? Sigma is the hard sphere diameter. Sigma is the closest that the centers of 2 molecules can get to each other if these molecules are hard spheres, so like billiard balls. Okay, so you break 6 bonds and you put a new molecule in. So this is the cavity. And you form 12 bonds. Which is going to give you positive 12 W sigmas. So by the powers of arithmetic, the net gain is 12 minus 6 is 6. W of sigma, which equals mu superscript I of the liquid. Now, if you can't picture this, I honestly have a hard time picturing this in 3 dimensions. It's a lot easier to picture it in 2 dimensions. So imagine that you had some close-packed system of circles in 2 dimensions. Where each contact point, and just pretend that these ones that I drew crappily are actually in contact. Each contact point is a bond, is a W of sigma's worth of potential energy. So in this case, in the case of 2D, if you want to form the cavity here, you have to break 3 bonds. Then you put a new one in, and you get 6 more bonds. So you break this cavity, and you break this bond, and this bond. That's 3. And then you put a new ball in, and then to see where the new ball would go, you just pick some other ball in here, and how many does it have? 1, 2, 3, 4, 5, 6. Same thing in a close-packed system in 3 dimensions. Okay, what is the connection between mu I liquid and W of sigma? It's some number like 6. It's between 1 and 10. Let's say it's around 6. And it really is around 6 for most systems. It's going to be a little bit more than 6 because we didn't consider multi-body effects of this molecule interacting with the sphere, with the next farthest away sphere. But most of the electrostatic potential energy is satisfied by the molecules that are closest to it. Let's use this to give us a quantity called the molar cohesive energy. The molar cohesive energy, or just the internal energy, the internal energy is capital U, and what this is minus 6 times Avogadro's number times W of sigma. Sorry, I called it NA the other day. I hope it's okay. We're going to call it N0 from now on for Avogadro's number. Okay, so this is the factor of 6 from here times Avogadro's number, so which has units of per mole, and this has units of energy. So really, we can get the internal energy of a material just based on this really crude estimate. Again, this is a crude estimate, but a crude estimate of its intermolecular pair potential. It's pretty cool because it's actually, in the next couple of classes, we'll figure out how to calculate these intermolecular pair potentials, from which you should be able to get some actually useful thermodynamic data. Generally, we're going to find that U is 4 to 6 times the bond energy. The bond energy is W of sigma, W at the hard sphere diameter. So this self-energy, we got in an easy way, but remember we calculated the self-energy of a gas last time. So just as a reminder, the self-energy mu superscript I, self-energies always have mu superscript I. In a couple minutes, I'm going to introduce mu with no superscript, which is the chemical potential. They're different. When you read the chapter, you're going to be really confused, but they're different. The self-energy mu sub I is the, I don't mean that in a judgmental way. When I first read chapter 2, I was confused by it for like an hour. Is the sum of the W of R's with all other molecules and the mu I of a gas is what we derived last time, and you were asked to derive it in 2 dimensions in your homework, which is the integral from the hard sphere diameter to infinity of W of R times rho 4 pi R squared dr, or minus 4 pi C, just some constant, which is usually going to be the van der Waals constant, over n minus 3 times sigma to the n minus 3. This is the same result as last class. And our W of R equals minus C over R to the n for R greater than or equal to sigma, for n greater than 3 for van der Waals forces, and the potential is infinity for radii less than the hard sphere diameter because of the Pauli exclusion principle. Okay, can we use the concept of self-energy to calculate anything? And the answer is yes. If we know what the difference in self-energy is from a molecule in one phase to a molecule in another phase, by the Boltzmann distribution law, we should be able to tell how those molecules segregate at equilibrium if we know the self-energy. Okay, so let's draw a beaker. Which has some liquid in it and has some chunk of some solid. And the solid dissolves a little bit. So these are particles that are now in solution from the solid. So this is a two-phase system at equilibrium. And this could be a solid or liquid. And in the solution phase, we can characterize its contents by X2, which is the mole fraction of the, you know what, why would I start with X2? Let's start with X1, huh? Okay. x1 is going to equal 1 for pure solid or liquid. And this is the mole fraction. It is the fraction of moles of 1 compared to of moles of the entire system. So 50% of 1 gives you a mole fraction of 0.5 by moles, not by mass. So for a solid, since it's all the same stuff, the mole fraction is 1, because all the moles are one thing. But we also have a self-energy, mu1 of I, which is the self-energy of the molecules in the solid. And that's going to be whatever it's going to be. It's not going to be 1. And then x2 is the mole fraction of the solute in the liquid phase, in the solution phase. And it's going to have a different self-energy term because it's the interaction of molecules of things other than itself is going to be different than the interaction of the molecules with the solid in its own solid. So again, the mu n's superscript I are the self-energy. X sub n's are the concentration in mole fraction units. So moles over moles. By the Boltzmann distribution, we can calculate the concentrations, the concentration in the solvent based on the differences in free energy, based on the differences in self-energy. So one way of writing this might be x1 equals x2 e to the negative difference in the self-energies between the two phases. Over kT, where K is the Boltzmann constant and temperature is the temperature. Or we could write this in another way, mu1 I plus kT natural log x1 equals mu2 I plus kT natural log x2. This is for two phases, but for a multi-phase system, we can just replace the indices with n's, mu n of I, or mu sub n superscript I plus kT natural log of the concentration and mole fraction of the species in the nth phase equals some quantity regular mu, plain old mu. Now, plain old mu is not the self-energy, but the chemical potential. And what the chemical potential embodies is the idea that molecules will move in a system and move between phases until the chemical potential is the same everywhere. the chemical potential is minimized at equilibrium between all the phases. So just like voltages, so electrostatic potentials move charges until, to the extent that they can, until the energies of the charges are at equilibrium. Chemical potential says if you have lots of molecules over here, not very many molecules over here, things are going to move until the energies of each molecule are the same, or until the chemical potentials are the same, which is going to rely on the energies, but also the concentrations. In other words, the energies and the entropies. So the molecules move until mu is the same everywhere. So this is the energy term that is a summation of all of the intermolecular pair potentials in the system. And this term, the K natural log of X sub n, is the ideal entropy term. Yep.
So would you be able to find, would you, in like a multi-phase system, does this mean that you could just solve for like any two phases and then you'd get, you'd be able to set any two phases equal to each other to figure out like the mole fractions?
If you set any phases equal to each other to get the mole fractions, yes, but you'd have to, I mean, one equation per unknown. So you'd have to know what the self-energies and one of the concentrations were in order to get the missing quantity, but yes. So we've seen other distribution laws like this, and we're not going to go into detail, although one of these will come up later. So the gravitational potential energy you can think of as a Boltzmann distribution, where the potential energy of an object at some height z minus the potential energy of the object at some height 0, so the ground level. Equals mgz, but the density of objects, say gas molecules in the atmosphere at z, will equal the density at the ground level times some decaying exponential that equals the potential energy at a given height, mgz minus mgz over kt. And this is the barometric distribution law. So gravitational potential energy in the atmosphere follows a similar distribution, but so does the concentration of charged molecules. Which says that in regions of two different electrostatic potentials, psi1 and psi2, you're going to have some reorganization of charges in order to minimize the energy of the system. So in this case, the electrostatic self-energy in region 2 minus the electrostatic self-energy of a molecule or ion in region 1 will equal E, which is the fundamental charge times the difference in electrostatic potential energies between the difference in electrostatic potential in two regions. So this would be like the voltage. Yes. Thanks. And this equals the density of charges in region 2. Or you can write this as the density of charges in region 2 equals the density of charges in region 1 times e to the minus e delta psi over kt. And this is the Nernst equation. How, what?
E exponentiates itself, and it's interesting. If you don't mind your keys, for sure.
I mean...
I see what you're saying. It's all right.
Okay, just to make sure that we're all on the same page here.
Yeah,
this is the exponential.
That's the charge.
Yeah, and this is the fundamental charge. Okay, can we calculate molecular parameters with this knowledge? Yes. Okay. If phase 1, this, by the way, is an aside. We're not going to talk about gravitation, although Israelishvili loves gravitation, or electrostatic potential energy until, we're not going to talk about this again until chapter 14. Yep. No, okay. So if phase 1 is a pure solid or liquid, then mu 1I equals mu 2I plus kt natural log x2, or x2 equals e to the minus mu 2I minus mu 1I over kt. And our problem, and this is one of the examples in the book, but it's a really good one, so make sure you read the discussion surrounding it, is estimate the radius of cyclohexane based on its solubility. What is cyclohexane? Cyclohexane is a stop sign. 6 carbon atoms and 12 hydrogen atoms. Given its interfacial free energy that it makes with water, which is gamma sub I. This is interfacial free energy of 50 millijoules per square meter, which is typical of a hydrophobic solute in water. So if you have salad dressing and you point to the interface, you can say that's 50 millijoules per square meter. interfacial free energy with water. And we're also given its solubility. And we're given its solubility in terms of molar, 7 times 10 to the minus 4 moles per liter, or big M with a line under it. But this is problematic because our X needs to be unitless, so we have to convert solubility in molarity to solubility in mole fraction. So X2 will be the solubility over the concentration of H2O, because this is not very soluble, so we can just take the concentration of H2O as being essentially all of the stuff in the system, because this is very sparingly soluble. So what we're going to have then is moles per liter over moles per liter. So 7 times 10 to the minus 4 molar over, what's the concentration of water in molarity? How many in a liter of water? 55.5. And this gives us a mole fraction of 1.26 times 10 to the minus 5. There will be some minor component of the cyclohexane, and if the solubility were significantly larger than this, we'd have to worry about it, but we don't have to worry about it. Yeah?
The first formula, mu 1I.
Yeah.
The last portion, should it not be ln x2 by x1? If we are using the same formula as what was given there.
So x1 is 1, so this term is 0. Good question. Okay, so what are we calculating? We have x2 equals e to the minus change in mu I between the two phases over kt, or natural log of x2 equals minus mu I over kt. Now, what is the change in energy? In this case, since we have the interfacial free energy, and if we approximate the cyclohexane in water as a sphere, in engineering we love to approximate things as spheres. If you're going to approximate it as a sphere, then the change in free energy is going to be the interfacial free energy that you create with one molecule dissolved in the cyclohexane. So minus 4 pi r squared, which is the surface area of a sphere, times the interfacial free energy over kt. So and it's not going to be that far off. So the conformation of cyclohexane in water isn't really a stop sign. It looks kind of like this, so-called chair or iron throne conformation. And it's going to flip inside and outside, and over time it's a sphere. Okay, so what are we solving for? Now we have something that we're solving for, the R. R is the radius of the molecule. That's what we were charged with doing, calculate the radius. So R equals natural log of x2 times kt over minus 4 pi times the interfacial energy, all under the square root, or minus 11.28 times this times kt, assume this is room temperature, which is 4.11 times 10 to the minus 21 joules. You're going to see this number appear over and over and over again, over minus 4 pi times 50 times 10 to the minus 3 joules per square meter, all under the square root, and we get a radius of 2.7 times 10 to the minus 10 meters for the radius of cyclohexane in water, where the literature value is 0.28 nanometers. Pretty good. Of course, we had some assumptions in here, but the basic theoretical framework is pretty good. Okay, cool. This quantity KT appears over and over and over again in the class. Now, KT is KT can be thought of as the amount of energy that's available at a given temperature to make stuff happen. So sometimes if you're doing a reaction or a process and you need it to happen and it doesn't happen at room temperature, you increase the temperature, so you increase the amount of energy available to make the transformation happen, which manifests in the Boltzmann distribution as this product KT. So it's worth talking for a minute about what this actually means and what its value is. So KT is called the thermal energy. And you can think about it as the ambient energy that is available to make stuff happen. And when we see Ks, we're talking about molecules. When we see Rs, we're talking about moles. What's the relationship between K and R? There's a factor of Avogadro's number difference between K and R. So K equals R, the universal gas constant, divided by Avogadro's number, and its value is 1.38 times 10 to the minus 23 joules per Kelvin. KT, where T is always 298 Kelvin, unless stated otherwise. Equals 4.1 times 10 to the minus 21 joules. This number is useful to have memorized, although you'll always be given a table that has all the constants. But why memorize KT or RT? because you might be in some scientific meeting where you're trying to come up with some drug compound or nanoparticle formulation, or you're going to be designing a battery or a microfabrication process, and someone says that the adhesion between this and this species in your system is 2 × 10 to the -22 joules. And you can say that will not survive at room temperature. That interaction will not be strong enough. So I would advise you to at least memorize the order of magnitude. Okay. Sometimes in optics, we're talking about electron volts. The energy of an electron when accelerated by 1 volt. And RT, so this one is also KT. So RT, or KT per mole, is also 2.5 kilojoules per mole. From the kinetic theory of gases, we're not going to, you don't need to be responsible for this, but we had that the average kinetic energy of a molecule in an ideal gas was 1/2 the average velocity squared, or 3/2 kT. Average kinetic energy of a molecule in an ideal gas. Some of you may have seen that before. Pretty sure everyone has, but it might be forgettable. It's like this board and that board are impossible to erase. Something about the nanostructure. It's always about the nanostructure. All right. We can use this concept of the thermal energy and intermolecular forces to predict how much energy is required to condense a gaseous phase into a condensed phase at a given pressure and temperature. So how strong must the IMFs be to condense molecules at a given temperature and pressure? And the solution will be to find the relationship between the cohesive energy and the boiling point. the cohesive energy U and the boiling point TB. Okay, so we're going to start with the self-energy of a molecule in the gas plus kT natural log of the mole fraction of the gas equals the self-energy of a molecule in the liquid plus kT of the kT times natural log of the mole fraction in the liquid. And the first thing that we can say to simplify this is that the mole fraction, is that the self-energy of a molecule in the liquid is going to be much greater than the self-energy of a molecule in the gas. So if we rearrange this and we ignore this one, so here's what we do to ignore things, is approximately equal to negative mu L of I equals kT natural log of the ratio between the mole fraction of the species in the liquid divided by the mole fraction of the species in the gas. Now this won't be obvious why immediately what to put for this, but how you can think about it is the ratio of the moles at a given volume so the ratio of the moles at a given volume, 1 mole of the liquid is something like maybe 20 milliliters. And the concentration of the gas, 1 mole of the gas will occupy 22.4 liters, something like that. Or you can think about it in terms of just divide this out. 50 moles per liter, and this one would be 0.044 moles per liter. And what you get is 22.4 over 0.02. So what you have then, if you just take the natural log of this ratio, is you get 7. What's the meaning of life? 7. Draw all that stuff, just 7. Okay. Minus mu Li equals 7 kT. Now we can multiply this by Avogadro's number. So we have minus n naught mu Li equals 7 n naught kT, but what's n naught times k? If we're talking about moles, and eventually we do want to get into mole territory so that we actually, because who knows what a molecule is, right? You can't touch a molecule. Is 7 RT. Next step is to divide by T. So divide by T, and we get minus Avogadro's number times mu Li over T equals 7 N naught K, or just 7R. Hold this thought. Okay, hold this thought. At TB, we have equilibrium. And we have the expression, the change in entropy upon vaporization equals the change in internal energy upon vaporization plus PV, where H of vaporization equals, you could also write it delta H from the of the gas minus delta H of the liquid. But we're going to write it the way that your book writes it. So these are deltas. These are deltas. So the internal energy is the energy required to create the state, which is a manifestation of all the intermolecular forces. So 6 times W of sigma equals mu, and then U equals Avogadro's number times, U equals Avogadro's number times mu. And this is the pressure volume work that was required to make room for the system. Against some externally applied pressure. By the ideal gas law, we can change PV into RT. But we're going to also use our definition of the internal energy of vaporization from the first chalkboard of the third chalkboard of the first beginning part of class today, from earlier in the class. Plus RTB. So this substitution was done using a definition of internal energy that we had from earlier in the class. This substitution is done using the ideal gas law at the boiling temperature, TB. We are going to divide by TB. So H of vaporization over TB equals minus N naught mu L I over TB plus R. Now this looks a lot like that I asked you to hold in your memory banks, and except that this is NET and this is TB, but that's fine because we're talking about TB. So this 7R and the whole thing is 8R. What does this tell us? It tells us that H of vaporization over TB is the change in entropy of vaporization by the Gibbs free energy equation at equilibrium. which is 8R. Now, this is a little profound, right? Because we don't know anything about the molecular details. And we're saying that the delta S of vaporization for any material is 8R. And R is always 8.314. No, I'm getting 8 and I'm getting R and pi confused. 8.3145, something like that. Actually, it's close to pi, huh? At least the decimals. Anyway, it's always a constant. It's always a constant. So this is this number is like 70 joules per mole Kelvin. The actual heat of vaporization or the actual entropy of vaporization isn't, it's a little more than 70 joules per mole Kelvin, but given the fact that every step in here involved a pretty gross simplification, it's pretty good. It's actually between 80 and 90 joules per mole Kelvin for most materials. So this is a crude estimate. Actual is closer to 10.5 R, or 80 to 90 joules per mole Kelvin. Incidentally, why didn't we have a delta here? So this is the delta V. Why didn't I have a delta V? And the delta V we left out because the volume of the liquid is negligible compared to the volume of the gas. So this is just the volume of the gas. Okay. Almost done for today. So this relationship is quite profound. It has a name. It's called Trouton's rule, named after Professor Rule. Trouton's rule, S of vaporization is approximately a constant, 80 to 90 joules per mole Kelvin. The value of mu of a liquid is usually about 9 kT per molecule, or 3/2, which is 9 divided by 6 kT per bond. So if you have an intermolecular pair potential, in order to predict that it's going to form a condensed phase at a given temperature, then its intermolecular pair potential better be above 3/2 kT. Probably it should be significantly higher than this. So the intermolecular pair potential for methane, which is a gas at room temperature, is about 1 kT. For water, it's about 10 kT. Your homework asks you to use Trouton's rule to calculate the entropies of vaporizations of various solvents, various liquids. Now, what Trouton's rule ignores is the fact that there is more than just configurational entropy. So the configurational entropy that comes into the equation by the mole fraction, so just where on a checkerboard you place the molecules, that's all we cared about here. But in a real system, molecules have rotational freedom. They have freedom to aggregate with each other in either the liquid phase or the gas phase. And what we're going to end up seeing is that some media have either positive or negative deviations from Trouton's rule depending on the specifics of the molecules in the system. So for example, water we know is heavily hydrogen bonded in the liquid. So when you vaporize water, do you lose more, do you gain more freedom than you would expect if they were just these unstructured solvent kind of balls in a ball pit? The answer is yes, because you break up those associations, you put them all in the atmosphere, and you had a relatively smaller solution phase entropy and the same gas phase entropy as for any other liquid. So you have a positive deviation from Trouton's rule. It's going to end up being like over 100 joules per mole Kelvin. And there might be other species that maybe form an ordered gas phase. Maybe the liquid phase is as disordered as any other liquid, but in the gas phase, for whatever idiosyncratic reason, those molecules form, say, dimers or other ordered structures that might give you a negative deviation from Trouton's rule and maybe a value of 60 as opposed to 80 to 90. But this will work for essentially all unstructured media that are unstructured in the liquid phase and the gas phase. So have fun with that problem, and I will see you on Tuesday.